Clausius-Clapeyron equation was derived by Clausius-Clapeyron by using Maxwell's second equation of thermodynamics, and this equation is depicting the rate at which the vapor must change with temperature for two phases to coexist in equilibrium. And it can be derived by using second equation, which is given by curly S, that is rate of change of entropy with respect to volume at constant temperature, which is equal to rate of change of pressure with respect to temperature at constant volume. This is second equation, Maxwell's second equation in the thermodynamics. If we multiply both sides by temperature, absolute temperature, then we get T into divided by volume at constant temperature, T times rate of change of pressure with respect to temperature at constant volume. In this equation, if we see that T times delta S, it gives us change in heat, and using this equation may be written as delta Q times equal to T times curly P over curly T at constant volume, where delta Q is the change in heat and delta V is the change in volume, and this total quantity gives the amount of heat absorbed or rejected per unit change in volume at constant temperature, and it is also called latent heat and denoted by capital L. And also delta V may be written as change in volume. That means if final volume is V2 and initial volume is V1, then change in volume may be written as this delta V. So if we write these values in this equation, then we get L over V2 minus V1 is equal to T times change in pressure with respect to temperature with constant volume. If we rearrange the terms here, we can write change in pressure with temperature keeping volume constant. Then we get, it comes out to be L divided by temperature and change in volume. And this is the equation which is known as Clausius-Clapeyron latent heat equation, or simply Clausius-Clapeyron equation. Clausius-Clapeyron equation or latent heat equation. And this equation provides us the rate at which pressure must change with change in temperature for two phases of a substance to coexist in equilibrium. Now this equation also explains the effect of pressure on boiling point. This effect of pressure on boiling point, because in this equation curly P over curly T at constant volume, that means change in pressure with respect to temperature is only positive. It is only positive if on the right hand side we have V2 minus V1 positive, or we can say, or if V2 is greater than V1. It means for vaporization of a liquid, for vaporization of a liquid, this equation may be written as change in pressure with respect to temperature for saturated state, or saturated state, will be equal to latent heat divided by temperature into volume of vapor state minus volume of liquid state. So this way we can rewrite this equation. Clausius-Clapeyron latent heat equation may be written for the vaporization of liquid this way, and for this condition it means V of vapor state, volume of vapor state should be greater than volume of the liquid state, and for that it means that the liquid must expand on getting the latent heat. That means delta P, if you increase delta P, then delta T should also increase, and if delta P decreases, then delta T should decrease. So or in other words, we can say increase in pressure raises the boiling point of the liquid, or decrease in pressure decreases the boiling point of the liquid. And that is why food is cooked fast in pressure cooker, because on increasing the pressure in pressure cooker, boiling point also increases. And it is also due to this equation we can show that it is difficult to cook at mountains than at plains, because on the mountains atmospheric pressure decreases and boiling point also decreases, and therefore cooking becomes difficult on the mountains. So that is about the Clausius-Clapeyron equation, which is derived by using this second equation of thermodynamics, which is Maxwell's second equation of thermodynamics. And we can say it is Clausius-Clapeyron equation is the application of of Maxwell's thermodynamic relations. Thank you for watching this video.